Module 6, Lecture A, Types and Identity. By the end of this lecture, you will be able to use type, instances, and is subclass to inspect and reason about object types and class hierarchies. Interpret ID values to understand object identity and lifetime in simple scenarios. And apply len to built-in containers and custom objects that implement the length protocol. Type checks and is instance. Exact type inspection. Exact type inspection means checking the specific class an object belongs to, rather than focusing on what it can do or which interfaces it supports. It is useful when you must clearly tell apart objects that seem similar, such as an integer versus a general numeric type, or a base configuration class versus one of its subclasses. By looking at the exact blueprint used to create the object, your program can make precise and reliable decisions in its logic. In a data processing pipeline, records can come in many forms, such as plain dictionaries, base data classes, and subclasses with extra metadata. At certain stages, you must check the exact type of each record so you can decide how to handle it. For example, only the base data class might be compatible with a legacy system, while subclasses need to be sent to a newer component that understands their additional fields. This careful type inspection ensures each object is routed correctly and that important differences between record types are not missed. Relying on exact type inspection can make code less adaptable because it treats a class and its subclasses as completely separate, so new types may be mishandled unless every check is updated. This strictness can be valuable when precise control is critical, but in more dynamic systems, it can limit flexibility and future growth. By understanding when to use exact type inspection, you can better balance strict type boundaries with a more flexible, behavior-based design. Python code. Exact type inspection. This lesson shows how to use exact type inspection with the type function on simple numeric values, and contrasts it with using instances for more flexible polymorphic checks. You will see that exact type checks require a value to be of one specific type, while instances can accept values from a type and its subclasses. By comparing these approaches on basic numeric examples, you can better understand how they behave. The goal is to help you decide when strict type boundaries are useful and appropriate in simple programs. We create 3 variables to show how similar values can have different types in Python. One holds the integer value 10, another holds the floating point value 10.0, and the third holds the Boolean value true. The integer and floating point values look similar, but are stored and handled differently, especially in terms of precision. The Boolean value is also stored as an integer behind the scenes, but it is used for logical decisions rather than numeric calculations. This setup highlights why understanding data types is important for predicting how Python will behave. In Python, you can use the built-in type function to find out the exact data type of a variable. For example, applying it to an integer, a floating point number, and a Boolean will show that their types are integer, float, and bool. Knowing these precise types is helpful for understanding how your data is being handled. It is especially important for debugging or when you need to enforce strict type boundaries in your code. We first check whether a value is exactly of the integer type. which confirms it is a strict integer and not just any numeric value. We then perform the same kind of check on a floating point value, which correctly reports that it is not an integer type, showing the distinction between integers and floats. Finally, we check a Boolean value against the integer type. Even though Booleans are implemented as a subclass of integers in Python, this strict comparison still returns false. Together, these checks show that exact type comparisons are important when you need precise control over which kinds of values your code accepts. The isInstance function is used to check whether an object belongs to a particular class or to one of its subclasses. When we use it on an integer value and ask if it is an instance of the integer class, it returns true because the value is indeed an integer. If we use it on a Boolean value and ask the same question, it also returns true, since in Python, Booleans are defined as a subclass of integers. This shows that isInstance takes inheritance into account. Unlike strict type checks that only match the exact class. Base config is a simple base class that does not define any methods or attributes on its own. It serves as a starting point for creating more specialized classes that inherit from it. By using this base class, you can build a clear hierarchy in object-oriented programs. This approach helps organize code and manage configurations in a scalable, structured way. Special config is a class that inherits from base config, so it automatically gains all of base config's properties and methods. This means special config can be used anywhere a base config is expected. This design lets you create more specialized configurations that extend a general base, supporting polymorphism and encouraging code reuse. We begin by creating a basic configuration object from the base config class, which serves as our general setup. Then we create a second object from the special config class, which is a more specialized configuration that inherits from the base one. These two related objects will be used to show how checking for an exact type differs from using an isInstance style check when working with class hierarchies. This explanation describes how exact type checking works when comparing two configuration objects. The code uses the type function to confirm that one object is strictly an instance of the base config class, not a subclass. It then checks another object, which is actually an instance of special config, and shows that it is not treated as the same type as base config under this strict check. This behavior is important when you need to enforce precise type boundaries and avoid treating subclasses as if they were the base class. The isInstance function is used to check whether an object belongs to a particular class or to any class that inherits from it. In this example, it tests whether the special configuration object is treated as a member of the base configuration class. Because the special configuration class is defined as a subclass of the base configuration, the check returns true. This shows that isInstance understands and respects inheritance relationships in a class hierarchy. This material explains the difference between exact type checks and polymorphic type checks in Python. It compares using the built-in type function, which requires an exact match and treats integers, floats, and booleans as distinct, with using the instance function, which also considers inheritance and therefore treats a boolean as a kind of integer. The script then introduces a base configuration class and a special configuration subclass to show that exact type checks see them as different, while instance treats the subclass as an instance of the base class. Overall, it shows that exact type checks enforce strict type boundaries, while instance is better when you want to work with inheritance and polymorphism in object-oriented code. Is-instance for polymorphism. Using the instance function for polymorphism means focusing on what an object can do rather than its exact class. Related classes, such as different shapes or payment methods, usually share a common interface through inheritance or an abstract base. By checking whether an object belongs to this broader family, instance lets your code safely accept any object that fits the required role while rejecting unrelated ones. This supports flexible, extensible designs where you can add new behaviors without changing existing logic. Using the instance check helps you design flexible systems where you can add new features without changing existing code. For example, in a reporting system that outputs text, HTML, or PDF, you define a general renderer type that all specific renderers inherit from. Your program only needs to know that an object is some kind of renderer, not which specific one it is. Once you confirm an object is a renderer, you can safely call shared methods such as those that format headers and footers. If you later add a new renderer, like one for slide decks, the existing code still works because it relies on the shared abstraction instead of individual subclasses. This programming style is important when combining components from large systems or external libraries. In scientific computing, different numeric types can share a common base, and a function can check whether an object belongs to this numeric family so it can handle them uniformly. The same idea appears in user interfaces, where buttons and sliders are treated as generic widgets, and in web frameworks, where requests and responses share a common ancestor. This approach enables polymorphism, keeping code safe and flexible by confirming that objects fit the expected hierarchy without depending on one specific implementation. Python code, instance for polymorphism. This section explains how to use the instance function to support polymorphic behavior in a family of renderers. You define a shared base renderer class, and then create multiple specific renderer subclasses that all follow the same rendering interface. By using instance checks, you can safely determine which objects belong to this renderer family and confidently call the shared rendering methods on them. This ensures consistent behavior across different renderer types, while still allowing each subclass to provide its own specific implementation. In Python, the ABC module lets you define abstract base classes, which are classes designed only to be inherited from, not created directly. From this module, we import the ABC base class and the abstract method decorator. An abstract base class can declare methods using the abstract method decorator to indicate that subclasses must provide their own implementations. This enforces a consistent interface across different subclasses while allowing each one to define its own specific behavior. The report renderer class is defined as an abstract base class, meaning it acts as a blueprint for other classes rather than being used directly. It relies on the abstract base class mechanism to require that all subclasses implement specific methods. In this case, the header rendering method is declared as abstract, so every subclass must provide its own version of it. This design guarantees that all subclasses share a consistent way to render headers, enabling polymorphic behavior across different types of renderers. This description explains that the report renderer class declares an abstract method called render body. Because it is abstract, any subclass of report renderer is required to provide its own version of this method. The method receives a content parameter, which represents the main part of the report that needs to be rendered. The use of a placeholder implementation simply signals that the base class does not define the behavior, and subclasses must override it to specify how the report body is actually rendered. We define a class called text renderer that inherits from a base class named report renderer, so it must implement the abstract methods required by that base. One of these methods is the render header method, which takes a title and returns a string formatted as a text header. In this implementation, the header is created by adding the phrase text header before the title. This gives text renderer its own specific way of rendering headers in plain text, fitting into a polymorphic design where different renderer classes can produce different output styles. This method defines how the body of a report is rendered in a text-based format. It takes the report body content as its input and returns a string that first labels the content as a text body, then appends the content itself. By doing this, the rendered output clearly indicates that it is using a text format. This is helpful in a polymorphic system where different renderers may handle the same report in different ways. The HTML renderer class is a subclass of an abstract base class called report renderer, so it must provide concrete versions of the abstract methods defined there. In this case, it implements a method that takes a title and returns it formatted as an HTML header using the Level 1 header tag. This gives HTML renderer a specific way to render headers in HTML format. It also fits into a polymorphic design where different renderer classes can each define their own rendering logic while sharing the same interface. The render body method belongs to the HTML renderer class and takes one input called content. It returns a string that places this content inside HTML paragraph tags. This means the text will be displayed as a proper paragraph on a web page and will follow standard HTML formatting for text. Inches renderer is a subclass of the abstract base class report renderer, so it must provide concrete versions of all abstract methods defined there. It implements a render header method that takes a title and returns a string that begins with the words inches report, followed by that title. This gives a specific way to format report headers for measurements in inches. It also fits into a polymorphic design where different renderer classes can be swapped and used in the same way. This method defines how the body of a report is displayed for the inches renderer class. It takes one input called content, which holds the main measurement value. The method returns a single formatted sentence that starts with the words measured length, then inserts the content value, and ends with the word inches. In this way, it clearly presents the data as a length measured in inches. In this example, we define a class called NotARenderer that is intentionally unrelated to the rendering system discussed earlier. Inside it, there is a method named something else that simply returns a message saying it is not part of the rendering context. The main purpose of this class is to act as an object that does not match the expected renderer interface. This allows us to see how an instance check can correctly ignore or filter out objects that are not valid renderers. The showReport function takes a renderer object, a title, and some content, and first checks whether the renderer belongs to the report renderer class. This type check ensures the renderer supports the required methods to build a report. If it passes, the function uses the renderer to create a header from the title and a body from the content, then prints the type of renderer being used, followed by the rendered header and body. If the object is not a valid report renderer, the function instead prints a message saying the renderer was rejected because it does not meet the required type. We create several renderer objects to show how a report handling function should accept or reject them. First, we instantiate a text renderer that handles plain text reports, then an HTML renderer that formats reports as HTML, and then an inches renderer designed for reports that use measurements in inches. We also create an object called NotARenderer, which does not belong to the renderer family and is included as an example of something the report handling function should reject. The showReport function is called several times with different renderer objects to demonstrate how it works. When it receives a text renderer, an HTML renderer, or a length renderer, it first checks that the object is a valid report renderer, then uses it to format the given title and content and prints the result in the appropriate style, such as plain text, HTML, or a custom inches format. When it is called with a stranger object that is not a valid report renderer, it detects this and prints a message rejecting the object instead of trying to render the report. This illustrates how the function enforces type checking before performing any rendering. This script illustrates polymorphism with a base class called ReportRenderer and 3 subclasses that each render reports in a different format: plain text, HTML, and inches. Each subclass defines its own way to produce a header and a body. A function called showReport accepts a renderer, a title, and some content, checks whether the renderer belongs to the report renderer family, and if so, calls its render methods to print the formatted report. If the object is not a valid renderer, the function prints a rejection message instead. Running the script shows that the 3 renderer subclasses work correctly, while an unrelated object is safely rejected, demonstrating controlled and safe polymorphic behavior. Prefer instance over type. When deciding what type an object is, focus on how it behaves rather than the specific class it comes from. By thinking in terms of broader categories, such as whether something acts like a data stream or a sequence, you take advantage of inheritance and polymorphism. This makes your code more flexible and able to work with new subclasses that may be added later. Overall, this behavior-focused mindset leads to programs that are easier to reuse and extend. Using flexible type checks helps your software evolve more easily. If you depend on one specific payment class, you must change your code whenever a new payment method appears. Instead, by defining a general payment abstraction, you can plug in new payment types without touching existing logic. This is like designing a road system that works for any vehicle, not just one model. By focusing on general capabilities, your code becomes more adaptable and easier to extend over time. Using behavior-oriented type checks, where you test whether something belongs to a broader category instead of matching an exact type, leads to better design and maintainability. Relying on strict type comparisons makes code rigid, discourages subclassing and compatibility, and can cause small changes to break many parts of the system. In contrast, broader checks keep the codebase open to extension, make it easier to integrate libraries, support mock objects in testing, and adapt to new domains. Over time, this approach helps your code stay flexible and easier to evolve instead of becoming resistant to change. Python code. Prefer instances over type. This section explains why using isInstance checks is usually better than checking for exact types. With isInstance, your code automatically accepts subclasses, so new payment types that inherit from a base payment class will still be recognized correctly. In contrast, comparing types directly only matches the exact class and ignores subclasses, which can break flexibility and extensibility. By comparing the behavior of type equality and isInstance with simple payment classes, you can see that isInstance leads to more robust and reusable code when working with class hierarchies. We define a class called payment method that includes a process payment method taking an amount in dollars. This method simply prints a message saying that a generic payment is being processed for that amount. The purpose of this design is to provide a basic structure for handling payments. Other classes can then extend this structure to implement their own specific payment processing behavior. This code defines a class called credit card payment that inherits from the payment method class, so it includes all the general payment features, but can also add its own. Inside it, there is a process payment method that takes an amount in dollars. When called, this method prints a message saying that a credit card is being charged for that amount. By doing this, it overrides the more general process payment method from payment method with a version specific to credit card payments. This code defines a gift card payment class that inherits from a more general payment method class. By inheriting, it automatically gets all the behavior of payment method, but can change specific parts. In this case, it replaces the process payment behavior with its own version. When that method runs, it prints a message that a gift card is being used for a given dollar amount. This gives gift card payments their own specific processing logic, separate from other payment types such as credit cards. The handle payment strict function takes a payment object and a dollar amount, then checks whether the object's type is exactly payment method. If it is, the function reports that the strict handler accepts the payment and calls the process payment operation with the given amount. If the object is not exactly of type payment method, the function reports that it rejects the payment. This design is very rigid because it only accepts objects of the precise payment method type and does not allow any subclasses. The handle payment flexible function takes a payment object and a dollar amount. then checks whether the object is an instance of the payment method class or any of its subclasses using a type check. If it is, the function announces that the flexible handler accepts this payment object and calls its process payment method with the given amount. If the object is not based on payment method, it announces that the flexible handler rejects it. This design allows the function to work with any subclass of payment method, making it more flexible than a strict type check that only accepts one exact class. We first create an object from the payment method class to represent a generic payment method. Then we create an object from the credit card payment class, which is a subclass of payment method, to represent a specific credit card payment. Using these two objects, one general and one specialized, we can compare strict type checking with more flexible type checking that uses the is-instance approach. The code first announces that the strict payment handler is being used with a base payment object, then calls the strict payment handling function with that object and an amount of 50. Inside this function, it checks whether the payment object's type is exactly the payment method type. Because the base payment object matches this type, the check succeeds. The function then confirms that the payment object is accepted and calls its process payment method to handle a payment of $50. We begin by printing a message to show that we are using the strict payment handler with a credit card payment. Then we call the strict payment handling function with the credit card object and an amount of $75. Inside this function, the code checks whether the payment object is exactly of the base payment method type. Because the credit card payment is a subclass rather than the exact base type, the strict handler rejects it. This example highlights the limitation of using exact type checks, which can incorrectly reject valid subclass instances. We begin by printing a message to show that we are using the flexible handler with a credit card payment, setting the context for what follows. Next, we call the flexible payment handling function, giving it the credit card payment object and an amount of $75. Inside this function, an is-instance style check is used to see if the payment object is a kind of payment method, which means it also accepts subclasses such as credit card payment. This illustrates how using is-instance for type checking supports inheritance and is more flexible than a strict type comparison. This script shows the difference between strict type checks and using instances in Python when working with inheritance. It defines a base class called payment method and two subclasses, credit card payment and gift card payment, each with a method to process payments. A strict handler that checks for the exact payment method type rejects subclass objects like credit card payment. In contrast, a flexible handler that uses instances accepts both the base class and its subclasses. This demonstrates that instances is usually preferred for type checking in object-oriented programming because it naturally supports inheritance. Subclass relationships. Checking subclass relations. In class hierarchies, it is important to know when one class is a more specific version of another, which is what checking subclass relationships means. This involves asking whether every instance of one class can also be treated as an instance of a more general class. For example, a surgeon is a kind of doctor, and a doctor is a kind of healthcare professional. But not every healthcare professional is a doctor. In programming terms, the surgeon class is a subclass of the doctor class, and this chain continues up the hierarchy. Understanding these relationships helps you know which operations are valid and what behaviors you can expect from objects of different classes. Understanding subclass relationships helps you reason about object identity more precisely. When you know an object belongs to a specific subclass, you can infer its particular characteristics and behaviors in addition to those of its general category. For example, recognizing a bus as a subclass of vehicle in a transportation simulation tells you it follows all vehicle rules, but also has unique features such as passenger capacity. This perspective lets you see the object as both a specialized entity and a member of a broader group. Subclass checks help you see how different objects are related in a system. For example, in a financial app, you might have a general account type with savings, checking, and investment accounts as subclasses. Even though each account has its own identity, they can be handled in the same way for tasks like calculating balances if they share this common base type. By checking subclass relationships, you can apply shared rules across these accounts while still allowing each one to keep its unique characteristics. Python code. Checking subclass relations. We want to show how simple subclass relationships work by using checks that tell us whether one class is a subclass of another. This helps us see how more specialized classes are connected to a common base class they extend or refine. By examining these subclass relationships, we can also reason more clearly about object identity, such as which objects belong to which class hierarchy and how they are related through inheritance. We define a class called vehicle that acts as a general blueprint for creating vehicle objects. Inside this class, there is a describe method that returns a simple description of the vehicle as a generic type with an unknown maximum speed. This basic design lets us later create more specific kinds of vehicles that inherit from the vehicle class while providing their own specialized descriptions. We define a class called car that inherits from a more general vehicle class, meaning car is a specialized type of vehicle and automatically gets its properties and behaviors. Inside car, we override the describe method so it returns a specific description that says the car has a maximum speed of about 100 miles per hour. By overriding this method, car objects provide a more detailed and customized description than other kinds of vehicles that also come from the vehicle class. We create a bus class that inherits from the vehicle class, meaning bus is a more specific kind of vehicle and automatically gets its properties and behaviors. Inside this bus class, we override the describe method to return a description tailored to buses. This description explains that a bus has many seats and moves at a slower speed suitable for city driving. By overriding the method, bus objects provide their own specific description, distinguishing them from other vehicle types that also inherit from vehicle. The cone uses a built-in function to check whether the car class is a subclass of the vehicle class. This function returns true when car inherits from vehicle. The program then prints the result to confirm this relationship. This helps illustrate the class hierarchy and how objects from these classes are related. We use the isSubclass function to check whether the bus class is a subclass of the vehicle class. This function returns true when the first class inherits from the second. In this example, it confirms that bus inherits from vehicle, so bus is a more specialized type of vehicle. Doing this check helps us understand the class hierarchy and how these classes are related through inheritance. We create two separate objects from the car class and store them in different variables. This shows that a single class can be used to make multiple distinct objects, each with its own identity and memory. We will then examine these objects to confirm that they both inherit from the vehicle class, illustrating how inheritance works in object-oriented programming. This line displays both the unique identifier and the class type of the object called car1. The identifier obtained using the ID function helps you distinguish this specific object in memory from other objects. The type function reports the class the object belongs to, which here is the car class. Together, they confirm that car1 is a distinct object and that it is an instance of the car class. We check the identity and type of the object called car2 to learn more about it. The identity function gives a unique number that represents where this object is stored in memory. The type function tells us that this object belongs to the car class. Together, these results show that car2 is its own separate car instance with a unique memory address. We are checking whether two objects, called car1 and car2, come from the same base class, which is vehicle. To do this, we use a type-checking function that tells us if each object is an instance of the vehicle class. When the function confirms this for both objects, it shows that they both inherit from vehicle. This demonstrates that car1 and car2 share the same base class relationship. The program calls the describe method on the car1 object, which uses the version of describe defined in the car class, instead of the one in its parent class, vehicle. This overridden method returns a short description of the car as a type of vehicle, with a top speed of about 100 miles per hour. That description is then printed together with the label car1 description to clearly show what the car1 object represents. This script uses a simple vehicle hierarchy in Python to show how subclassing and polymorphism work. It defines a base vehicle class and two subclasses, car and bus, each with its own description method. The script confirms that car and bus inherit from vehicle, then creates two separate car objects to show they are distinct instances that share the same base class. Finally, it calls the description method on a car object, demonstrating that the subclass can override the behavior of the base class while still fitting into the same overall interface. Abstract base classes. Abstract base classes focus on shared capabilities instead of specific implementations. They describe a role, such as being iterable or acting as a sequence, without tying it to a particular concrete type. This lets different classes, even from separate libraries, be treated as the same kind of thing, as long as they provide the required methods. In large systems, this abstraction supports more flexible, scalable designs where what an object can do matters more than its exact class. Abstract base classes are used to check whether an object or class follows a particular protocol or interface, instead of focusing on its exact type. They let you ask if something behaves like a container that can be measured or indexed, even if you do not know whether it is a list or a custom structure. By linking concrete classes to an abstract base class, you create a shared framework that tools and developers can rely on. This makes it possible to test whether a class acts like a sequence or a mapping based on its behavior and supported operations, rather than its place in an inheritance tree. Abstract base classes help separate what an object is from what it can do. Two objects may come from different concrete classes and have different identities, yet still be treated as instances of the same abstract base class if they share the same interface. For example, configuration and settings objects from different libraries can both behave like mappings even though they live in different places in memory and exist for different lengths of time. Thinking this way lets you clearly distinguish identity questions, such as whether two references point to the same object, from capability questions, such as whether an object can play a particular role, which improves design flexibility and understanding of object relationships. Python code, abstract base classes. This lesson shows how to use abstract base classes to define shared behavior roles that different concrete classes can implement. You will see several specific classes that all act like the same kind of container, even though their internal details differ. The focus is on how these classes can be treated uniformly through their shared abstract behavior. Finally, you connect these behavior roles with actual object identities by using the identity function together with type checking, so you can see both what an object is and what abstract role it plays. The code imports abstract base classes for mappings and sequences from the collections module, so we can describe and test how objects behave, such as whether they act like dictionaries or lists without caring about their exact types. These base classes define common behaviors that different objects can share. If an object fulfills the role of a mapping or a sequence, it can be used wherever that behavior is expected. This makes it easier to write flexible, reusable code that works with many kinds of objects as long as they follow the same interface. We first create a configuration dictionary that stores values such as width and height in inches, using Python's standard mapping type. Then we define a custom object using the type function that behaves like a mapping by providing methods to get items, iterate, and report its length. This custom object is set up so that it always returns the value 42 for any key, has an empty iterator, and reports a length of 1. As a result, it acts like a mapping in how it can be used, even though it is not a normal dictionary. We begin with a simple list of the numbers 1 through 4 as a basic example of a sequence in Python. Then we define a custom sequence type called feat sequence using a dynamic class creation approach. This custom sequence provides a method that reports its length as 3 and another method that returns each element as 3 times its index, representing distances in feet. Together, these examples show that you can create objects that behave like sequences without relying on the built-in list type. We use the isInstance function with abstract base classes to check whether different objects follow certain behaviors. First, we test if a regular dictionary behaves like a mapping. Then we check if a custom settings object also acts as a mapping. Finally, we verify that a regular list behaves as a sequence. These checks show that different objects can share the same abstract behavior even if they are implemented in different ways. The code first checks whether the custom sequence object truly behaves like a sequence by using a type check against the abstract sequence base class. This confirms that the object plays the same role as a sequence, even though it is not a built-in list. It then uses a function that returns the unique identity of the configuration dictionary in memory. This identity value distinguishes that specific dictionary from all other objects in the program. This code uses the identity function to obtain unique memory identifiers for 3 different objects: a custom mapping-like object, a regular list used as a sequence, and a custom sequence-like object. These identity values show that each object is distinct in memory, even if they play similar abstract roles. This is useful when you need to confirm object uniqueness and understand how different containers are allocated and managed in memory. The code uses the InstInstance function with the mapping abstract base class to check whether both a regular dictionary and a custom mapping-like object behave as mappings. It then prints a message explaining that, even though these 2 objects have different identities, they share the same abstract role. This demonstrates that different implementations can still conform to the same interface or behavior, as long as they meet the requirements of the mapping role. This script shows how Python's abstract base classes can define shared behavior roles, such as mappings and sequences, across different objects. It tests a regular dictionary and a custom object to see if they both behave like mappings, and a list and another custom object to see if they both behave like sequences. The results confirm that the dictionary and custom mapping object both satisfy the mapping role, and the list and custom sequence object both satisfy the sequence role. The script also prints their identity values to emphasize that even though these objects are distinct, they can still share the same abstract behavior. This demonstrates the flexibility of abstract base classes in letting different objects exhibit similar behaviors. Handling non-class inputs. When working with class hierarchies, do not assume every input is a valid class object. Inputs may come from user data, network messages, or other sources, and could be strings, numbers, or null values instead of classes. Passing these directly into code that expects a class can cause errors. To avoid this, always check and validate inputs before using them, and design your code so it fails in a clear and predictable way when it encounters unexpected types. When building a plugin system for a data analysis tool, you may ask developers to register new components by providing a class that follows a specific interface. In reality, they might instead pass an instance, a class name as text, or even something completely unrelated. If your system blindly assumes every input is a valid class, it can crash or silently accept bad plugins that fail later. By first checking whether the input is actually class-like, you can safely reject invalid values and return clear error messages that explain what was received and what was expected. When code expects a class but receives something else, the interface should make its expectations and behavior clear. You can strictly reject invalid inputs with a clear error. Try to adapt them, such as turning a string into a class, or fall back to a default behavior that does not rely on class hierarchies. The right choice depends on context, with stricter handling in secure or critical systems, and more flexible handling in exploratory environments, like data science notebooks. Thoughtful handling of these cases helps keep type relationships clear and prevents subtle bugs. Python code. Handling non-class inputs. This section focuses on safely handling invalid inputs when checking whether something is a subclass. It emphasizes that the code should detect when a given value is not a real class and respond with clear, informative error messages. The behavior should be demonstrated both with correct class inputs and with several kinds of incorrect values, so learners can see the contrast. Overall, the goal is to make subclass checking robust, predictable, and easy to debug when users pass the wrong type of input. We import the abstract base classes for sequences, mappings, and iterables from the collections module, so we can test whether other classes are subclasses of these types. In this script, the sequence class is especially important because it lets us check if something behaves like a list or a tuple. This setup is crucial for a function that examines subclass relationships and helps the code handle different kinds of input in a consistent way. This function checks whether a given input is a subclass of the sequence class. It first confirms that the input is actually a class type. If not, it reports that a class was expected and returns false, so only valid class objects are processed. It then uses a subclass check to see if the class inherits from sequence, reports the result, and returns it. If this check raises a type error because the input is not a proper class, the function catches the error, reports what went wrong, and returns false, handling invalid inputs in a controlled way. We create a new class called MyList that is based on the built-in list type. Because it inherits from the standard list, it automatically has all the usual list behaviors and properties. At the same time, we can add our own methods or attributes to customize it for specific needs. This allows MyList to be used anywhere a normal list is expected, while still supporting extra program-specific features. The demo inputs function illustrates how a subclass checking helper responds to different kinds of inputs. It first shows a correct case by passing a valid class called MyList. It then demonstrates several incorrect cases, passing an instance of that class instead of the class itself, passing the class name as a string, passing an unrelated class such as the dictionary type, and finally, passing the special value none. Together, these examples show how the function distinguishes valid class inputs from various invalid ones and provides clear feedback for each situation. The demo inputs function is used to show how the sequence subclass checking function responds to different kinds of inputs. It first demonstrates a correct case by passing in a class that is a subclass of list. It then shows several incorrect cases, an instance of that class instead of the class itself, the class name as a string, an unrelated class such as a dictionary, and finally, the special value none. Together, these examples highlight how the function distinguishes valid class inputs from invalid ones and provides informative feedback for each situation. This script shows how to safely check whether a given input is a subclass of the sequence type from the collections module. It defines a function that first confirms the input is actually a class, and if not, it reports that the input is invalid. If the input is a class, the function then tries to determine whether it is a subclass of sequence while catching any type errors. A demonstration function runs this check on several examples, including a custom list class, an instance of that class, a string, the built-in dictionary class, and a none value. The results confirm that the custom list class is a valid subclass of sequence, while the other inputs trigger clear error messages, illustrating robust handling of incorrect types. Identity and length. Understanding object identity. In programming, when we talk about objects, we care about both what they are and which specific instance they represent. Object identity tells us whether two references point to the exact same instance in memory or just to separate objects that happen to look the same. For example, two lists with the same student names may appear identical, but are still distinct objects with different identities. This concept is similar to owning one particular copy of a book among many identical copies. Identity allows the interpreter to distinguish between instances that share the same type and content at a given moment. Object identity is about tracking a specific instance as it changes over time, while value describes what that instance currently represents. Mutable objects, like a shopping cart, can change their contents but keep the same identity. Immutable objects, such as numbers or text labels, act as fixed values, and their identity can vary depending on how memory is managed. The essential idea is that identity follows the particular object you can update or observe, and value is the current data it holds. When working with objects in a program, it is important to distinguish between identity and value. Asking for a container's length is asking about its current state, not which specific object it is. Two different lists can have the same length if they hold the same number of elements, even though they are separate objects. If you add or remove elements from one list, its length changes, but its identity as that particular object does not. Understanding this difference helps you reason about how objects behave when they are shared, copied, or updated in your code. Python code, understanding object identity. This topic explains how to demonstrate object identity using the identity function and equality comparisons. You should show that two separate lists can have the same contents but still be different objects in memory, meaning they are equal in value but not identical. You should also show that when you change the contents of a single list, its identity stays the same, proving that the object itself persists even as its data is modified. Together, these examples clarify the difference between comparing values and comparing object identities. We create two separate lists that both contain the names Alice, Bob, and Kara. Even though their contents are identical, they are different objects stored in different places in memory. This setup highlights the difference between object identity and equality in Python. The lists are equal in value, but each one has its own unique identity because they were initialized separately. We first display the value of the first list along with its identity number, which represents its location in memory. We then do the same for the second list. Even though the two lists contain the same elements, their identity numbers are different. This shows that they are stored in different places in memory, which is an important idea for understanding object identity in Python. The code first checks whether two lists have the same contents by using the equality operator, which compares the values of their elements. It then checks whether the two lists are actually the same object in memory by using the identity operator. This second check determines if both variables refer to the exact same location in memory, meaning they are not just equal in content, but are literally the same object. We modify a list by adding a new element named Dave to the end, which changes the list's contents but not its underlying identity in memory. The location where the list is stored stays the same even though its data is updated. After appending the new element, we print the list and its identity number to show that the contents have changed, while the identity, as reported by the identification function, remains constant. This illustrates the idea that some data structures can be altered in place without changing their memory identity. The program shows that the second list stays unchanged and then prints its identity number using the function that reports an object's unique identifier. This confirms that the list has kept the same identity in memory, even though its contents were examined. The example highlights the difference between an object's identity and the data it holds. This script illustrates object identity and mutability in Python using two separate lists that start with the same contents. When their values and identity numbers are printed, the lists look the same but have different identities, meaning they are stored as distinct objects in memory. A comparison shows they are equal in content but not identical as objects. After an element is added to the first list, its contents change, but its identity stays the same, while the second list remains unchanged in both content and identity. This demonstrates how Python distinguishes between equality of values and identity of mutable objects like lists. Aliasing and shared state. When you measure length in a program, you are measuring the size of the object in memory, not the variable itself. This matters because several variables can refer to the same object, a situation called aliasing. If two variables point to the same list, asking for the length through either one gives the same result. The length function simply follows the reference from the variable to the underlying object and reports that object's size, regardless of which variable name you use. With mutable objects, aliasing is important because several variables can point to the same underlying data. If two variables refer to the same list and you add an item through one of them, the change is visible through the other as well, including the new length. This can be surprising if you imagine variables as separate containers, but it is more accurate to think of them as labels attached to a shared container. When the shared data is modified, all labels show the updated state, revealing the shared nature of the object. When designing custom objects that report a length, it is important to understand aliasing and shared state. If your collection wraps another structure or exposes internal data, its length can change because of actions taken elsewhere. For instance, a view that represents part of a dataset will change in length when the underlying dataset changes, even if you never touch the view directly. This kind of shared state is powerful in collaborative or dynamic applications, but you must reason carefully about how and when length can change, since a stable variable name does not guarantee a stable number of elements. Python code, aliasing and shared state. This material explains how aliasing works when two variable names refer to the same list. When both names point to one shared list object, any change to the list through one name, such as adding or removing elements, will affect what you see through the other name. As a result, the length of the list appears to change for both variables at the same time. This demonstrates that they are simply different aliases for a single underlying list. We create a list of student names and then assign that same list to another variable, so both names refer to the exact same list in memory. When we check their lengths, they match because there is only one underlying list object. This situation is called aliasing, where two different variable names point to the same data. As a result, any change made through one name will automatically be reflected when we access the list through the other name. We first check whether the two variables, student's main and student's alias, refer to the same object in memory by using a test that tells us if they point to the exact same place. Then we use a function that returns the identity number of the object referenced by student's main, and we do the same for student's alias. If these identity numbers are the same, it confirms that both variables point to the same list in memory. When we add a new student named Kara to the list using the main reference, we are changing the single shared list that both the main and alias references point to. Because they both refer to the same underlying list object, any change made through one is immediately visible through the other. As a result, when we check the lengths of the main list and the alias list after adding Kara, they are the same. This demonstrates that both references are simply different names for the same updated list. When we add the name Dave to the list using the alias, we change the same underlying list object. This shows that both the main variable and the alias refer to exactly the same list in memory. After the append operation, printing the lengths of both lists gives the same result. The identical lengths confirm that there is only one shared list that now includes Dave. We finish by printing the list stored in the main student's variable to show its final state after all changes. Because the main student's variable and the alias both refer to the same underlying list, any modification made through either name appears in this final output. This illustrates how aliasing works in Python and how shared references cause updates in one place to affect the same data everywhere it is referenced. This script shows how aliasing creates shared state in Python lists. A list of student names is created, and a second variable is made to point to the same list, so both variables reference the exact same object. This is confirmed by checking that their identities match. When a new name is appended through either variable, the change appears in both, and the list length increases for both at the same time. By the end, all added names appear in a single shared list, demonstrating that modifying one alias affects the same underlying list. Length protocol basics. In programming, the length of an object means how many elements it contains. The length protocol is a shared rule that lets different containers, such as strings, lists, and dictionaries, report their size in a consistent way. For example, a string reports how many characters it has, while a list reports how many items it holds. Because they all follow the same protocol, You can ask for the length of many different container types in the same way, without needing to know how they are implemented internally. The length protocol is not limited to built-in containers. You can also use it with your own custom objects. For example, a playlist in a media app or a shopping cart in an online store can report how many songs or items they contain. By providing a length, these objects can behave like standard containers, so you can check whether they are empty, compare their sizes, or enforce limits. This makes custom objects easier to work with, in the same way you work with lists or sets. The length of an object should always match its current contents, so the reported number of elements is clear, stable, and consistent with what you would get by iterating over it. For mutable containers, this length can change as items are added or removed. But at any given moment, it should accurately reflect the elements present. This consistency is important for reliable loops, condition checks, and other logic. When designing custom containers, you must decide what counts as an element and ensure that any change to the container correctly updates this count, since other parts of your program may rely on it for tasks like managing resources and giving feedback to users. Python code, length protocol basics. In this lesson, we explore how the length function works with both built-in containers and custom objects. We see that different kinds of containers, such as lists or other collections, can all answer the same basic question about how many items they contain. We also connect the idea of length to iteration, showing that length reflects a stable and meaningful count of elements that you can loop over. Overall, the goal is to understand length as a consistent way to measure the size of many different kinds of objects. We create a shopping list that holds several items such as eggs, milk, bread, and butter to show how a list can store multiple strings. We then define a short text message that simply contains the phrase, "Hello, world," which can be used for basic text analysis or manipulation. Finally, we make a collection of unique postal codes, including values like 90, 02, 10, 10,000, and 1, and 60,614, to demonstrate how a set stores distinct integers without duplicates. The length function can be used to find the size of different types of data containers. For a shopping list, it returns how many items are in the list. For a message, it returns how many characters are in the text. For a collection of zip codes stored as a set, it returns how many unique zip codes there are. This shows that the same length function works consistently across lists, strings, and sets to report their sizes. We define a custom class called playlist that works like a container, similar to built-in lists or sets. Its constructor, or initialization method, sets up each playlist with a name and a collection of songs. The name is stored as given, and the songs are converted into a list, so the behavior is consistent even if another kind of iterable is provided. With this design, a playlist can be used much like standard Python containers, allowing you to get its length and iterate over its songs. This method defines how to get the length of a custom object by returning the length of its internal list of songs. As a result, the object can be used with the standard length function just like built-in containers. This makes the custom object follow Python's length protocol and allows it to work wherever the length of an object is required. This method specifies how to loop through a playlist object by returning an iterator over its list of songs. With this iterator in place, the playlist can be used directly in loops and comprehensions. In other words, it lets the playlist behave like any built-in iterable in Python. We create a playlist object called road trip and initialize it with 3 songs to show that this custom class can act like a built-in container. We then use the standard length function to get the number of songs in the playlist. The result confirms that the playlist class correctly supports the length protocol by returning the count of items it holds, just as built-in lists or strings do. We add a new song called Song D to the playlist, which changes the playlist's internal state by increasing how many songs it holds. After this, we print the updated song count. When we ask for the length of the playlist, it calls the custom length method defined in the playlist class. That method returns the current number of songs, now including the new one. This shows that the length of a custom object can update automatically as its contents change. We create a list comprehension that iterates over the road trip playlist, using the playlist's iteration behavior to collect all its songs into a new list of visited songs. Then, we compare how many songs were visited with the playlist's reported length. If these numbers match, it shows that iterating over the playlist covers exactly all the songs it contains. This confirms that the playlist's iteration and length are consistent with each other. This script shows how Python's length protocol works for both built-in and custom objects. It first uses the length function on a list, a string, and a set to illustrate that the same operation can measure the size of different container types. It then defines a custom playlist class that supports the length protocol by providing its own length method, so an instance of this class behaves like the built-in containers when its length is requested. After adding a song to the playlist, the new length reflects the change, and iterating over the playlist visits exactly as many songs as its length reports, highlighting the link between length and iteration. In this lecture, you learned to use type, isInstance, and isSubclass to inspect and reason about object types and class hierarchies. Interpret ID values to understand object identity and lifetime in simple scenarios. And apply len to built-in containers and custom objects that implement the length protocol. In the next lecture, Lecture B, we will go over dir vars help.
Thank you for your attention. See you all in the next lecture.